Hello and good day, Algebra. I'll be going over the math packet with you, math packet number 7. Let me go ahead and expand this here so we can get the full page. We've gone over this in class already in 2 of the classes, but ACC, I think this is your first look at it. So kind of give you how to start each question, things to think about, and if you have any questions on it, you can see me or recommend turning in it early so that I can correct it. It is due February 16th. Note the due date there. Still about 2 weeks away. So this first question, Ian is entering a math contest. He's working on the particular problem, and this is the problem. The integers greater than 1 are arranged 4 in each row in 5 columns as follows. So we begin with 2. Let me go to the right, 2, 3, 4, 5. Skip column E. And then second row, start with 6 in column E, go to the left, 6, 7, 8, 9. Then down in row 3, 10, 11, 12, 13. Down in row 4, 14, 15, 16, 17. And the question is, if this pattern is continued, in what column would the number 1002 fall in? And my hint to you on how to start this is eliminate the columns 1002 absolutely cannot be in. So here's what we want to focus on. We want to look at the numbers in each column and look for patterns. Right off the bat, you might notice that columns B and D contain only odd numbers. 1002 being even, it's going to be impossible for 1002 to fall in column B or column D, so we can eliminate those. Okay? And then in class, we also talked about column C, in the sense that column C has all multiples of 4, 4, 8, 12, 16, next to be 20, 24, 28, etc. And so we looked at, does 4 go into 1002 evenly? Is 1002 a multiple of 4? And we decided no, it is not. Just a second. Let me... All right, we are back in. Okay, so as we were saying, column C only contains multiples of 4. 4 does not go into 1002. Therefore, 1002 cannot be in column C. So really, we're looking at column A or column E. And we look at the numbers in column A. We see that from 2 to 10, we're increasing by 8. From 6 to 14, we're increasing by 8. If we continued this pattern just in the next row, row number 5, 18 would go here, right? Then 19, 20, 21. Again, we see this increase of 8. So what you could do here, and it's not very efficient, but what you could do is continually add 8 to plus 8 is 10, plus 8 is 18, plus 8, plus 8, plus 8, plus 8, and see if you eventually get to 1002. Okay? If you do, then you know that 1002 is going to be in column A. If you don't, then you know that 1002 will be in column E. You can do the same thing here. Okay? This next number that will be in column E is 22, and again, it's an increase of 8. But like I said, that's not very efficient. That could take a while. So is there another way that you could essentially do the same thing, but more efficiently? And that is where I will leave you with this one as far as how you want to take it from here. The next question we have, Cameron invited 17 friends to his party. He assigned each friend an integer from 2 to 18 and kept the number 1 for himself. So we know that Cameron is number 1, and each of the 17 friends are 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 18. During one dance, Cameron being a very observant person, he noticed that the sum of each couple's numbers was a perfect square. Okay? What was Cameron's partner's number during this dance, and why wasn't I invited to the party? It sounds very mathematical, something I might like to be at. So here's Cameron, number 1. If during this particular dance, the couple's numbers, the sum is a perfect square, it means that, if Cameron's dancing with person number 3, 1 plus 3 equals 4. 4 is a perfect square. That is a possible option. Cameron's dancing with person number 5. Well, 1 plus 5 is 6. 6 is not a perfect square. So we know that Cameron can't be dancing with number 5. So there are only a certain number of options here that work out. Sums that add to be perfect squares. And the perfect squares that we'll be focusing on here are 4. The next perfect square is 9. 4 times 4 is 16. 5 times 5 is 25. And we realize that we don't have to go to 6 times 6. Because if the two largest numbers are partners, 17 and 18, 17 plus 18 is 35. That's the largest possible sum that we could have. So we don't need to go to 36 here because it's impossible to have a sum that large with 18 people. Okay. So we looked at, well, who could Cameron be dancing with? We already said 3 because 1 plus 3 is 4. Cameron could dance with person number 8 because 1 plus 8 is 9. Cameron could be dancing with person number 15. I'm going to make these a little bit closer together here so I have more room to write over there. 15 because 1 plus 15 is 16. But we're not going to be using the perfect square of 25 here because there's no number 24. Okay. So we only have 3 options for Cameron's partner here. So then we went to person number 2. 2 can't make a 4 because 2 plus 2, that'd be dancing with him or herself, and that doesn't work out. But 2 plus 7 equals 9, so it could be dancing with person 7, or it could be dancing with person number 14, 2 plus 14 being 16. Again, we're not going to make it to 25, so for person number 2, we are done. Person 3 could be dancing with Cameron, who is person number 1. 3 plus 6 makes 9, so that is an option. 3 plus 13 is 16, so that's an option. And again, we aren't going to get to 25. Then we continue this on. Person 4 could be dancing with 5 or 11. 6 could be dancing with 3 or 10. 7 could be dancing with 2 or 9 or 18. Okay. And now we can finally use that 25. 7 plus 18 equals 25. And it was here that we started to realize that we've got a match, right? Because that person 18 here, 18 being greater than 4, greater than 9, greater than 16, the only possible way to get a perfect square sum with 18 is if 18 and 7 are dancing together. Okay? Which means that 7 cannot be dancing with 2 and 7 cannot be dancing with 9. Right? We then went to person number 8. We said, well, 8 could be dancing with Cameron. Can't dance with him or herself to make 16, so that's out. But then 8 could be dancing with 17 to make 25. And it was here that we again realized that 8 and 17 have to be a match because 17 being greater than 4, 9, and 16, the only perfect square sum that 17 can partner up with is 8. So we have another match. And here's where we realize the value of going through all these numbers is because knowing that 8 cannot dance with Cameron, that means back up here in our Cameron row, Cameron cannot be dancing with number 8. And so we've already eliminated one of those 3 options. 8 is not the match. And so we're working with only 3 or 15. So the trick here is to go through the rest of them, numbers 9, 10, 11, 12, and start to realize, okay, this person, these 2 people have to be a match because of whatever reason, right? It's the only option, or you've eliminated everyone else they could be dancing with, and eventually you'll eliminate enough people to be able to say that, okay, Cameron is dancing with 3, or Cameron is dancing with 15. Okay, so a very logical approach to this one. Writing it out, looking at the options, using logic to say this has to be true, this can't be true, and eventually narrowing it down. All righty. Here we have the 5-card challenge in the spirit of Christmas. You have an ace to work with here. We love aces because they're ones, and we love ones because there's so much you can do with it. Excuse me. You can multiply by 1, divide by 1, take something to the power of 1. It's not going to change the value of the expression or the equation. So you can really rack up a lot of points quickly by using that ace. Equivalent equation. So the given equation, 30x minus 12y equals 24. This being an equation with an x and a y variable, your process is going to be similar to what you did in the previous packets, where you, you solved for x, and then you saw if that x was a solution to the other equations given. If it was an equivalent equation. If it was not a solution, then it wasn't. Similar thing here. 30x minus 12y equals 24, you're going to be looking for a value for x and y that makes this equation true. What's an ordered pair on this line? And we just finished up a unit on graphing, on lines, on ordered pairs, on solving for various things. So you can kind of look back to that and decide, how am I going to identify an ordered pair on the line? You could manipulate the equation. You could graph it. You could guess and check, right? There are lots of different options here. But that's essentially what you are going to be doing. Does an ordered pair that works in the given equation work in the others as well? Okay? Make sure you are defending your answer there. Moving on to the shaded area section. Okay, what do we have here? We have a rectangle, and then we have 3 semicircles, 2 of which are congruent, the one on the left and the one on the right. So really together, they make a full circle. And our job is to find the area of that shaded section. So similar to other shaded area questions we've had before, we're going to start with the area of the entire figure, okay, which the figure is the rectangle, right? And that formula is base times height. And then we're going to subtract the area we don't want. So if we start with the whole thing and remove those 3 half circles, what we're left with is going to be the shaded area. So your game plan for that one might be, the area of the rectangle, which is the whole thing, minus the area of the circle up on top, which looks like that, minus the area of the circle on the left, which looks like that, minus the area of the circle on the right, which looks like that. Okay? And that formula, that calculation, is going to result in the area of the shaded region. So we already have the formula for the area of a rectangle written here. The formula for the area of a circle is pi r squared. And like we've needed to do in past packets, since we don't want a whole circle here, in this first one, we only want half of that circle. The formula here is going to be pi r squared divided by 2, right? Because pi r squared would give us the area of a full circle with a diameter of 4 here, but we don't want that other part that the formula gives us. We divide by 2, and that's going to give us just that half circle. For the other 2 circles, the ones are congruent. You can find their areas individually, or just think of it as a whole circle, combine them together and go at it that way. But then your percentage, which is part divided by whole, in this context, that's equal to the shaded region divided by the total area of the figure. So your answers for the first 2 lines here are needed to find the answer for the third one. Part divided by whole. Next up, we have our pattern block page, okay? And for algebra, your job is to complete the table and calculate how many red blocks will be in the 10th figure. We're going to start to be working with some patterns that increase very quickly, okay? As you can see here, we're starting with just 1 block in figure number 1 here. And by figure 4, we're already, we're increasing rapidly, right? So the nice part about this is that that yellow column is very consistent. There's only one yellow block. Right? The pattern is really with the red blocks and how they increase. And what we talked about in class was this total block section is going to be a really nice tool for you because we are dealing just with squares here. So in figure 1, there's one yellow block, 0 red, and one total block. Figure 2, if you look at it, is a 3 by 3 square, which means that there are a total of 9 blocks. Figure 3 is a 5 by 5 square, or 25 blocks. Figure 4 is a 7 by 7 square, or 49 blocks. And the question that I asked the class was, what do you notice about those numbers going down the line in that total blocks column? 1, 9, 25, 49. Well, we notice that they're all perfect squares, and they're found by taking 1 squared, 3 squared, 5 squared, 7 squared, and so we predicted that the next block, figure 5, will be 9 squares, which is 81, right? And that kind of follows the pattern here. And we realized that, hey, if we know the total blocks, and we know how many yellow blocks, there's always one, finding the number of red blocks is just basic subtraction. 9 minus 1, there are 8 red blocks in figure 2, and we can verify that by counting them. 25 minus 1, there are 24 blocks in figure 3. Again, verify by counting. And 49 minus 1, there are 48. Might not want to, but you could verify that by counting. And that got us to very efficiently predict the number of red blocks in figure 5, which would be 80. Okay, 81 minus 1. So continuing these patterns throughout the table is a really slick way, realizing we're dealing with squares here and that perfect square pattern to move our way down to figure 10. You don't need to worry about this section here. That is for geometry only and will be explained in the geometry packet. Our final solid that we'll be talking about for surface area and volume is a sphere, okay? And we've got this sphere, radius of 9. Our first task is to draw a net of the figure. And how spheres work, this is like a ball, okay? The widest part is the middle here, kind of think about the equator of the Earth, okay, wraps all the way around. And then as you go up the sphere towards the top or down the sphere towards the bottom, my arrows are getting closer and closer. We are losing surface as we go up the sphere and down the sphere. So the net of a sphere is a rather interesting one. It's 4 leaf-shaped sections that all connect in the middle. And remember, I got a D in art when I was a lad, so forgive my drawing skills here, but that's not too bad. Okay. And this equator that I outlined in red here originally, now that goes all the way around the circles. That is the same distance as if we were to measure across those 4 leaves. Okay. And the reason why we are tapered at the top and the bottom is because, like I said, as we move up the sphere or down the sphere, we lose surface. We lose area. Okay? And so that would be your net. And the formula for surface area, of course, it includes pi, because anything with circles, anything related to circles uses pi. It also uses the radius. Okay? It's 4 pi r squared. The surface area of a sphere is 4 pi r squared. When I learned this growing up, I was expecting some really complicated, especially coming off of cones and cylinders. Those have a lot of pieces to it. 4 pi r squared doesn't seem that bad. And if you look for the connection with circles, our formula for the area of a circle is pi r squared. The surface area of a sphere with the same radius is just 4 times as great. I find that interesting. Okay, so 4 pi r squared is the formula for the surface area of a sphere. That calculation can go down there. Continuing with spheres, we move now to volume. And of course, volume, surface area, where it's the surface on the outside of the figure, okay? The volume is how much space is inside the figure, okay? So the formula for the volume of a sphere, kind of two ways you can write it. 4/3 pi r cubed, or you can use 4 pi r cubed divided by 3. Both formulas do the exact same thing. But notice that we are now cubing the radius rather than squaring it. So for this particular sphere, the calculation that we're going to use, and I'll use the second formula here, 4 pi times 9 cubed divided by 3. Okay, and that will give us the volume of the figure. For algebra, your task is, what is the radius of a sphere with half the volume of the original sphere? So the original sphere has the volume that you wrote in that line. You want to take half of that and then solve for the radius. Okay, half of that and solve for the radius. So whatever that volume is, right, after you take half of it, you're going to set that equal to our formula and solve for r. Okay, what value for r is going to make that formula equal the volume, half of the original sphere? Okay. Clearly, I did not bring my calculator to this video to do some of these calculations for you, so you can take it from here. But that's kind of your game plan for it. All right. Next one, math exploration, the Collat's conjecture. So mathematical discoveries weren't reserved for those who lived in ancient times. Number relationships are still being discovered in the modern age. Considering the following. Step 1, choose a positive integer. I've done that for you down here with 12 and 17. For each of these, we're going to go to step 2, which says if the integer is even, divided it by 2. My editor's fired. Divide by 2. And if it is odd, multiply it by 3 and add 1, which is more or less the expression 3n plus 1. So starting with 12, since 12 is even, we're going to divide that by 2. And our next number in this sequence is going to be 6. Okay, 6 also being even, we'll divide that by 2 again, and we have 3. 3 being odd, we are going to apply it to our expression 3n plus 1, multiply it by 3 and add 1. 3 times 3 is 9, plus 1. The next number of the sequence is going to be 10. Okay. Now we're back to an even number again. So divide it by 2 to get 5. It's odd, so 5 times 3 plus 1 is 16. 16 is even, so divided by 2. 8 gets divided by 2. 4 gets divided by 2. 2 gets divided by 2. And we're at 1. Okay? And here's where, when you do this on your own, you can stop. Because once we get to 1, 1 being odd, we would multiply by 3 and add 1. We still get back to 4 again. Well, half of 4 is 2. Half of 2 is 1. And we're going to be we're getting kind of stuck in this loop of 4, 2, 1, 4, 2, 1, 4, 2, 1 forever. It's just kind of a never-ending cycle. Okay? So we're going to do the same thing with 17. 17 is odd, so we're going to multiply by 3 and add 1. That brings us to 52. 52 divided by 2 is 26. 26 divided by 2 is 13. 13 times 3 plus 1. 39 plus 1 is 40. Divided by 2 is 20. Divided by 2 is 10. Divided by 2 is 5. You probably see the pattern here in relation to the one up above. 5 being odd, multiply by 3, add 1, that brings us to 16. And then 8, 4, 2, 1, 4, 2, 1, 4, and we're in that never-ending cycle. Okay? So the reason why this is a conjecture is something that has been proven to for all tested cases, but not all possible cases. So computers have tested the Collat's conjecture and found it true for all starting numbers up to that, which is really big. Okay. And over the years, several awards have been offered to anyone who could prove or disprove the conjecture, meaning prove that it does work for all cases, even those that have not yet been tested, or find a number it doesn't work for. Prove or disprove it, but it remains open to this day. So if you're sitting at home and you're bored, you can try and tackle this. See if you can come up and win that award. So your job is to try some on your own. You're choosing 5 starting numbers. Those numbers must be greater than 10. And you need a combination of either 2 odd and 3 even, or 3 odd and 2 even. So you can't just pick all even numbers and get there quickly. Okay. 2 must be odd, 3 even, or 3 odd and 2 even, and all greater than 10. And you can't choose 12 and 17, obviously, because we already did those. Okay. That is your math exploration. Next up, mean, median, and mode. A couple packets ago, I had you track the number of hours of sleep that you get for 7 consecutive nights and find the mean, median, mode of that. Kind of similar, only now I'm focusing on screen time. Okay. In the table below, record how many minutes, so it must be in minutes, don't put hours, minutes you spend on each of the devices listed every day for 7 consecutive days. So if you haven't started this yet, start tonight. Okay. And day 1, you can put the date, or just day 1, 2, 3, 4, 5, 6, 7. And how many minutes did you spend on the phone today, or your tablet, or your computer, or on the TV? Okay. And some of the questions that came up in class, does your school device count? The answer is yes, that is screen time. And if you say, well, I don't know how much time I spent on my computer in the school day. Well, if you use your computer for all of Mr. Olson's class, you just put down a 45. If you took a computerized test in Mrs. Chalmers' class, but you finished early, maybe put 30. Okay. I don't need, down to the exact minute. You can have a little freedom to round there if you're not quite sure, but do your best to keep track of it. If you spend the last 5 minutes of math class playing your computer games, then that 5 minutes counts for your computer time. Someone asked, well, what if I'm, playing video games? What does that count towards? Well, if you're playing on your computer, that'd be computer time. If you're playing on the TV, that would be your TV time. If you're playing on a console where it's handheld, like a Game Boy, if you know what Game Boys are, or the Switch or whatever, you can count that as a tablet time. Okay. Some folks said, well, I don't have a tablet. Okay, that's perfectly fine. Then it's zeros across the board for you. Okay. But whenever you are in front of a screen, you need to be keeping track of how much time you spend. And your job in algebra is to calculate the mean, median, and mode for each device. And then on average, this is your answer part here, on average, what percentage of each day do you spend using screen time? If you spend, on average, if your mean, okay, for all of your screen time together is 12 hours, that's a lot, by the way, but if it is, then 12 hours out of a 24-hour day, on average, you spend 50% of your day in front of a screen. Okay? That's how you calculate that. And finally, we have the polyomino question, everybody's favorite, no doubt. You're looking to see where in the figure on the right these 10 figures are. And just remember, they are not turned, they're not rotated, they're not flipped. As they appear on the left is exactly how they appear there on the right. And that is packet number 7. It is due February 16th. If you have any questions, please feel free to ask me. Don't wait until the last weekday to start this, especially since you have to track your screen time usage for 7 days. I recommend you turn it in early so I can give you feedback, get it back to you, and make any necessary corrections. But there you go, packet 7. We'll end the video here, and everybody have a tremendous day.